to determine the predominant intermolecular forces, we should always have the clear list of the possible intermolecular forces in our mind. So from the strengths, for the strongest strength to the weakest strength, the typical intermolecular forces include ion, that's between ion particles, like sodium plus cation and chloride minus anion. So the interaction between sodium chloride and sodium cation and chloride anion is ion-ion interactions. So the next on the list is dipole interaction. This typical intermolecular forces are between two polar molecules. So the dipole interaction is between polar molecules. They are neutral, but they are polar molecules, therefore they have dipole moment, showing as the separation of the charge inside the molecule. The next on the list is ion dipole. For example, if we have ion, either cation anion can interact with dipole moment from the polar molecule. For example, here, plus we have a negative on this side, which is attracted to these positive charges. So after that is ion induced dipole. That if we have ion and we have a neutral molecule, for example, carbon monoxide, nonpolar neutral molecule, and charge can induce dipole. That induced dipole can interact with charged molecule or charged particle. Okay? Then after ion-induced dipole can also induce a dipole moment in other molecules. So therefore, in this case, if we have plus minus a dipole moment at a polar molecule and placed close to our nonpolar molecule, the dipole moment can also induce dipole in this nonpolar molecule, that they can interact with each other. Then the next one is dispersion. This is mainly between nonpolar molecule, and this is universally exist and also is the weakest. So if we compare the strengths, actually from ion dipole all the way through, the strongest is ion. The second strongest, it should be ion dipole. After that is dipole, then ion-induced dipole, dipole-induced dipole, dispersion, generally speaking. And also, there are the special dipole interactions, which is called hydrogen bond. And hydrogen bond form is atom A bound with its hydrogen, and we have this interaction with atom B. A and B can only be nitrogen, oxygen, and fluorine. So we should always have this list in our mind. Then we can determine what's the predominant intermolecular forces. Predominant. We should have predominant listed in here. Predominant means there's many forms of the intermolecular forces. Which one is the most important one? Okay, most important one means the strongest. If you have ion, then we will not consider dispersion interaction because it's so weak compared to ion. So therefore, to determine the predominant intermolecular forces, we need to decide, do we have ion? If no, do we have the polar molecule or non-polar molecule? If we have ion, then we have ion, or ion with dipole-induced dipole. If we don't have ion and we have polar molecule, we may have a dipole-dipole. And if we don't have a dipole, polar molecule, there's no dipole moment, then we'll have dispersion. And also, we also always keep in mind, do we have a hydrogen bond? Okay, let's put this into action. First, what is the predominant intermolecular forces in each of the following substances? Solid carbon dioxide, and from the Lewis structure and from the VSEPR theory, we know that carbon dioxide has this linear structure and it's non-polar molecule. Therefore, there's no, the dipole moment is 0. Do I have ions? No. Do I have dipole moment? No. So what's the predominant intermolecular forces in this case? We have only one choice: dispersion. And it's pretty weak. How about liquid sulfur dichloride? If you work out the Lewis structure of sulfur dichloride, you figure out this molecule has band structure, and there's 2 lone pair on sulfur and 2 sulfur chloride sigma bond. So now, first, do we have our first question is, do we have ions? No, we don't have ions. But do we have dipole moment? Do we have, is this polar, non-polar? Of course, this is polar molecule. So there's no ion. This is the polar molecule. Therefore, the predominant intermolecular forces should be dipole. Of course, there should be dispersion, interaction among them as well, but that is much weaker than dipole-dipole interactions. Then the next one is magnesium chloride dissolved in liquid sulfur dichloride. So in this, it means what's predominant intermolecular forces between magnesium chloride with sulfur dichloride. Because we know sulfur dichloride, we have dipole-dipole interaction among them. And now the first question is, do we have ions? Yes, we do. We have magnesium chloride, we have magnesium 2 plus cation, chloride minus anion. And we have polar molecule, sulfur dichloride, that's the dipole moment in these molecules. So now we have ion and dipole. So therefore, the predominant intermolecular forces between this ion and dipole should be ion-dipole interactions. And the last one listing here, carbon dioxide dissolved in sulfur dichloride. The carbon dioxide, do we have ion in this list? No, we don't have any ions. Then, do we have a polar molecule? Yes, we have a sulfur dichloride, it's a polar molecule, and we also have carbon dioxide non-polar molecules. So the predominant intermolecular forces between this polar molecule and this non-polar molecule should be what? First, should that be ion? No, we don't have ions. It's not ion. Would that be dipole? No, we have a non-polar, polar. Between these two, not dipole. Then do we have dispersion? Yes, we do have a dispersion. But do we have, before that, we have non-polar, polar. Then we should have a dipole, induced dipole. That should be stronger than dispersion. So therefore, the predominant intermolecular forces in this case between carbon monoxide and sulfur dichloride should be dipole-induced dipole interactions. Alright, now let's move on to the next. list. So again, it's another list. What's the predominant intermolecular forces in each of the following substances? Oh, carbon dioxide, we have learned that. It's nonpolar. There's no ion, no dipole moment. It's nonpolar molecule, so therefore the predominant intermolecular forces for carbon monoxide simply is dispersion. Okay, then how about this liquid methanol? So the liquid methanol has this H3CH2OH. If you're not familiar with this, it's carbon connect with 3 hydrogen, another carbon connect with 2 hydrogen, connect with oxygen, connect with hydrogen. So we should get a sense that this is polar molecule. There's no ion here, therefore there's no ion involved interactions. And this is polar molecule. There's a dipole moment. But we have oxygen and hydrogen. As a polar molecule, yes, we have a dipole interactions. But with oxygen and hydrogen formed like this, we can imagine that we can have this kind of interaction. If you circle this, and we actually have hydrogen bond, and we know that generally speaking hydrogen bond is stronger than dipole interactions. So therefore in this case predominant intermolecular forces for liquid methanol is hydrogen bond. And we have talked about liquid sulfur dichloride. In this case, the predominant intermolecular forces among this molecule is simply dipole. Why is that? Because there's no ion involved. This molecule is a polar molecule, and apparently we couldn't form hydrogen bond. There's no hydrogen in here at all. So we have its dipole interactions. And again, we just talked about magnesium chloride dissolved in liquid sulfur dichloride. It is ion dipole. In the last case, carbon monoxide dissolved in the carbon dioxide dissolved in the sulfur dichloride. It is dipole, induced dipole. So we have talked about it in the previous slides. So now let's move on to this list. In the homework, the first 11-10 list the type of the intermolecular forces that exist between molecules in each of the following species. So in this case, we should list all the types of the molecular forces that exist. Exhaust list. So first, benzene. From our list, what do we have? Do we have ions? No, we don't have ions. And benzene is nonpolar molecules. And from the class, we should know that benzene has this hexagon structure. It's totally symmetrical. There's no dipole moment in this structure. So therefore, it's nonpolar, no ions, no dipoles. So the only possible intermolecular forces for benzene is dispersion. And the next one, CH3Cl, chloromethane. The Lewis structure of chloromethane should be this carbon at the center. We have a chlorine and also carbon bound with another 3 hydrogen, and the central carbon has tetrahedral configuration, and the hybridization state or hybrid orbitals of the central carbon is sp3. So you can get a sense that this molecule, although it is symmetrical, it is polar molecule. Again, there's no ion involved. It's a polar molecule with a dipole moment. The predominant intermolecular forces should be dipole dipole. And also we have a dispersion interactions, but here we just list the dipole-dipole intermolecular forces for this compounds. That should be fine. And in the next one, phosphorus trifluoride. So if you work out the Lewis structure, you will figure out this molecule has this so-called trigonal pyramidal structure, similar to the ammonia, NH3. And this molecule, it is polar molecule, and there's no ion, so therefore there's no ion involved. This is a polar molecule, and therefore the predominant intermolecular forces for this molecule, again, it is dipole. And the next one, sodium chloride. Do I have ion here? Yes, that's all we have. We have sodium cation chloride ion. So therefore, the predominant intermolecular forces in here, it is ion, pretty strong. How about carbon disulfide? Carbon disulfide listed here is actually similar to carbon dioxide. It has linear structure, and a carbon form double bond with 2 sulfur on either side. So first, do we have ion? No, we don't have ions. There's no ion involved. Do we have dipole moment? No, we do not have dipole moment. There's no dipole-dipole interactions. This is nonpolar molecule. So therefore, the predominant intermolecular forces for this species, again, is dispersion. Okay, that's the end of this problem. Let's move on to the next one. So the next one is a little bit different. The homework level 12 in chapter 11. Which of the following species are capable of hydrogen bonding among themselves? Okay, hydrogen bonding. To form the hydrogen bonding, we need to have A bound to with hydrogen, have this dotted interaction with B. A and B can only be either nitrogen, oxygen, and fluorine. So only in this form can be considered as a hydrogen bond. So first, methane, C2H6. Can we have a hydrogen bond here? Let's look at this. We have hydrogen, yes. Do we have a nitrogen, oxygen, or fluorine? Not at all. So therefore, no, we cannot have hydrogen bond. The next one, hydrogen iodide, Hi. Yes, we do have hydrogen. But do we have any of this nitrogen, oxygen, fluorine in hydrogen iodide? Of course not. So therefore, we cannot have hydrogen bond in this species as well. The next one, potassium fluoride. Oh, we don't even look at this. There's no hydrogen at all. No hydrogen bond. The next one is barium hydride. Again, we don't have any of the nitrogen, oxygen, fluorine. Only hydrogen is not good enough. So therefore, we do not have hydrogen bond in this species as well. The second to the last, acetic acid. So it looks like we should have the hydrogen bond because we have oxygen and hydrogen. And the answer is yes. And to be more specific, we have CH3 group carbon double bond with oxygen and with this OH group. And of course, we can have the hydrogen bond among them like this. This is the hydrogen bond. So therefore, the answer is yes, we can have the hydrogen bond. The last one, ammonia, NH3. Can we have a hydrogen bond? Do we have a hydrogen? Yes. Do we have a nitrogen? Yes. The answer seems yes, we can have the hydrogen bond. And yes, we have NH3. We can bond it like this. Okay, cannot draw there, but in this part, this can be considered as a hydrogen bond. And the answer is yes. In ammonia, yes, we can have hydrogen bond. Alright, let's move on. So the next one is arranging the following in order of increasing boiling point. What is the predominant intermolecular forces? What type of the crystal of these compounds could form as a hint? So essentially, the stronger the intermolecular forces are, the higher the boiling point, because it's required more energy to break the intermolecular forces and therefore to have the liquid form into steam. So essentially, we need to order this species based on their intermolecular forces. Okay, first, rubidium fluoride. What kind of a compound is this? It's metal, rubidium, and fluoride, a non-metal, fluoride. So metal, non-metal, we have ionic compounds. The predominant intermolecular forces is ion. And then carbon dioxide, we have talked about this many times now. It is non-polar molecule. There's no ion involved, so therefore predominant intermolecular forces is dispersion. And the next one, methanol. We have this OH group. Apparently, it can form the hydrogen bond. So therefore, the predominant intermolecular forces here is hydrogen bond. Although we do have dipole-dipole interactions, but hydrogen bond is a little bit stronger than the dipole-dipole interactions. So therefore, we list hydrogen bond as the predominant intermolecular forces. And the last one, bromomethane. Similar to chloromethane, it is polar molecule, and we do not have ion. There's no ion involved. There's no ion involved in intermolecular forces, and this is polar molecule, and apparently we cannot form hydrogen bond because we do not have a nitrogen, oxygen, or fluorine. So therefore, predominant intermolecular forces is dipole. Now, based on our understanding, the strongest predominant intermolecular forces among these four should be ion. So therefore, this compound should have highest boiling point. So A has the highest boiling point. The next one, among dispersion, hydrogen bond, dipole, and we know that hydrogen bond is more or less generally speaking, is stronger than dipole. So therefore, the next one should be hydrogen bond, which is C. After that, it should be D, dipole interaction. The weakest, as always, is dispersion, which is B. So therefore, the increase in boiling point, we should have A as the highest boiling point, C the second, D the third, B, carbon dioxide is the last one. To compare the boiling point, we essentially need to compare the strength of the intermolecular forces. The stronger the intermolecular forces they have, the higher the boiling point they have. So the first pair is neon and xenon. Neon, xenon, they are all noble gas. They are single molecule, monoatomic molecule. They are neutral. So therefore, they do not have charge. There's no ion-ion interactions involved. They do not have a dipole moment. They are all nonpolar. So therefore, there's no dipole-dipole interactions. So therefore, the only possible intermolecular forces they have is dispersion. But they all have dispersion interactions. How can we compare which one has the stronger intermolecular forces? To compare this, we need to compare the so-called polarizability. Means which one is easier to be induced to produce dipole. To compare that, we simply compare the size and the number of electrons. Neon, xenon. Which one is bigger? Apparently xenon. In neon, we have 10 electrons, and xenon, we have 54 electrons. So therefore, in general, xenon is more likely to be induced dipole, and it has higher polarizability, and therefore xenon has stronger intermolecular forces or stronger dispersion interaction than xenon. So in this case, the boiling point of neon is smaller than boiling point of xenon. And next one, carbon dioxide and carbon disulfide. We have talked about this in previous slides. They both have linear structure. They are both nonpolar. Therefore, the predominant intermolecular forces in both cases are dispersion. Similar to the problem 1, we need to compare the polarizability of these two molecules. So which one to compare the polarizability? We'll look at the size and number of electrons. So oxygen, carbon, oxygen, sulfur, carbon, sulfur. Which one is bigger? Yes, sulfur is bigger than oxygen and has more electrons. Therefore, carbon disulfide has a higher polarizability than carbon dioxide, and therefore it has a stronger intermolecular forces or stronger dispersion intermolecular forces, and therefore has higher boiling points. So the boiling point of carbon dioxide is smaller than the boiling point of carbon disulfide. The next pair, methane and chlorine gas. Alright, we know that methane has tetrahedral structure, is symmetrical, is nonpolar. So therefore predominant intermolecular forces, still dispersion, and chlorine gas Cl2 is also nonpolar molecule, and therefore dispersion is the predominant intermolecular forces. Again, we need to compare the polarizability between these two molecules. How about to compare this? We need to look at the size and the number of electrons. So methane, 1 carbon, 4 hydrogen, and 2 chlorine. Sounds like the 5 atoms together should be larger than the 2 atoms. That's probably true. But how about the electrons? We have 6 electrons in carbon, 1 each oxygen. So therefore, in total, we have 10 electrons in molecule 1 methane, but we have 17 electrons in each chlorine. So total, we have 17 times 2, 34 electrons in chlorine. So our gas should be comparing 10 electrons, 34 electrons. The 34 electron molecule probably has higher polarizabilities. So our gas in this case is boiling point of methane probably is lower than boiling point of chlorine gas, because chlorine has the stronger dispersion interactions due to its higher polarizabilities. Okay, the last one, the next one, fluorine gas and lithium fluoride. So this is actually much easier, because fluorine gas F2 apparently is nonpolar molecule, and therefore dispersion is a predominant intermolecular forces among these molecules. But lithium fluoride, it is metal, non-metal. We have this is an ionic compound, so therefore ion-ion interaction is the predominant intermolecular forces. It is much stronger than dispersion. So it's no-brainer in this case. The boiling point of fluorine gas is much smaller than boiling point of lithium fluoride. Okay, the last one is a little bit tricky. Ammonia, H3, and phosphorus trihydride. So from the Lewis structure, we know that they are all has this trigonopyramidal structure. Trigonopyramidal structure. Okay. and therefore we can see they are all polar molecule. They have dipole moment, and the predominant intermolecular forces in these two cases should be dipole-dipole interactions. And we need to sort of compare the dipole moment. The stronger the higher the dipole moment they have, the stronger the stronger intermolecular forces they have. And it's actually hard to tell which one has the higher dipole moment. But if we think more carefully, we notice that we have a nitrogen and hydrogen. With nitrogen bound with hydrogen, there's a possibility that we could form so-called hydrogen bond interactions. So right here, and we know that hydrogen bond interaction in general is stronger than dipole-dipole interactions, which is true in this case. So therefore, ammonia with hydrogen bond interactions, which is stronger than the phosphorus trihydride intermolecular forces. That's once again, hydrogen bond is stronger than dipole-dipole interaction in here. So therefore, the boiling point of ammonia should be higher than phosphorus trihydride. The reason, again, intermolecular forces for this species is hydrogen bond. It is stronger than intermolecular forces for this species, which is dipole-dipole interactions.